Okay, thank you very much, Michael, for having me here and for the kind introduction. As you said, my name is Katharina Dunst. I'm the head of the cycling department at the Institute of Applied Training Science and also work as a performance analyst for the German Rowing Federation. And today I'd like to share some thoughts on a new approach to the indirect assessment of VLMX. So what's the starting point? The maximum rate of blood lactate accumulation, or VLMX, as we heard before, is often used as a surrogate of maximal glycolytic power, and it's closely linked to sprint performance. Typically, it's estimated by measuring blood lactate accumulation during the lactic phase of short anaerobic all-out efforts, usually lasting 10 to 15 seconds. Our research now focuses on a key problem in performance diagnostics. In practice, using anaerobic sprint tests to measure VLMX often leads to validity issues, mainly due to the high degrees of freedom in execution, measuring, and calculation, as we heard several times today. And since we in our institute here rely on VLMX for many mathematical models, switching to the proposed parameter VLA peak is not an option for us. So that's why we started looking for alternative methods to improve the current gold standard. And today I want to share one of these ideas with you. The central question of this study is whether it is possible to determine VLMX from the observed formation of lactate over time and without having to measure it directly. Therefore, we goes into the energy share approach, which assumes that the total energy output is always the sum of the three metabolic components named the alactic, lactic, and aerobic energy contributions. When we now rearrange the equation, we can isolate the lactic energy contribution, which allows us to calculate the blood lactate accumulation, delta BLC, and derive the lactate formation rate, or VLA, by dividing the blood lactate accumulation by time. So now our idea was to use this approach in a maximal cycling sprint, which is long enough to show all key metabolic responses of an athlete, like a step response in system theory. Here too, but now in a time-dependent manner, the time course of total metabolic energy supply reflects the sum of the changing contributions from each energy system. Building on this idea I showed before, if we now know the total energy as well as the lactic and aerobic contributions over time, we can determine the time course of lactic energy supply and then calculate the time-dependent accumulation of blood lactate. By taking the derivative of the blood lactate accumulation over time, we obtain the time course of the lactate formation rate during the sprint. And based on the lactate formation rate function, we can now determine its maximum value and the corresponding time point. So let's recap. As an interim result, we can state the following. Using the energy share approach can be used to successfully determine the lactic energy contribution over time. And knowing this, we can calculate VLMX based on the time course of the derivative of blood lactate accumulation. However, looking closer at this method, there are some problems. First, it requires at least 3 maximal sprint tests to collect enough data. Second, it relies heavily on interpolation and curve fitting, which can lead to errors or bias. And third, when our data quality is very high, this method becomes unnecessary since the delta BLC over time can be identified without complex modeling. Therefore, our approach only makes sense if we can calculate VLMX from only a single sprint test. Therefore, we have to reformulate the original question to the version it is possible to determine the time course of VLA from only a single maximal sprint. To do that, we need different types of information. We have to know the electric energy supply over time. We have to know the aerobic energy supply over time, and of course, the total energy expenditure during the entire sprint. So let's check these requirements. First, let's have a look on the time course of the electric energy supply. Its total contribution can be estimated from the fast component of excess post-exercise oxygen consumption, named epoch. And additionally, the time course can be reconstructed using near-state data or derived mathematically. Second, the aerobic energy supply over time can be calculated from continuous measurements of VO2 and VCO2, typically via spirometry. Third, we have to know the total energy expenditure over time. Here, the total energy expenditure at the end of the sprint can be calculated as the sum of the total electric, lactic, and aerobic energy contributions. And finally, the time course of total energy expenditure can be determined if the time-dependent gross efficiency is known. Thus, eta over t, the gross efficiency, which changes over time during the sprint, is critical to model the dynamic energy supply based on only a single maximal sprint. In this context, we recently investigated whether changes in efficiency during a maximal sprint can be predicted. Here, our results show that these changes are proportional to the cadence normalized power output over time, called P max over T, which means that they can be directly derived from the power data, knowing the individual fatigue-free force velocity profile. If you're interested in more details, feel free to check out the related publication. Now we are ready to put our idea into practice. In our study, 17 professional track cyclists performed 2 maximal sprints in an isokinetic mode at a frequency of 120 RPM, lasting 12 and 60 seconds. Each sprint was separated by at least 30 minutes of passive rest, and we collected data on time, power output, and cadence, as well as blood lactate before and after each sprint, and respiratory gases for up to 13 minutes post-exercise to assess epoch. In our study, the 60-second sprint served as the data basis for our new approach. The 12-second sprint was used for validation reasons, and we also conducted a RAM test to identify potential predictive parameters. Here I show you an overview of each calculation step and the key parameters we used to estimate VLMX indirectly. Now let's take a closer look at each step. Firstly, based on the fast component of epoch, the difference between maximal post-exercise BLC and pre-start values and the VO2 and VCO2 data during the 60-second sprint, we can calculate our starting grid points for model calibration. If we now know the fatigue-free force velocity profile, we can also calculate the cadence normalized power output over time and use the constant to model how gross efficiency changes over time. If we know that, we can now calculate the time-dependent total energy supply. By using further information on PCR dephosphorylation from NIRS or by defining mathematical constraints based on the fatigue-free time span, we can reconstruct the time course of PCR during the sprint. If we now subtract the lactic and aerobic energy contributions from the total energy expenditure, we get the surged lactic energy supply. By taking the derivative, we get the time course of the blood lactate accumulation rate. And from this, we can now calculate both the VLMX and the time it takes to reach it. We can also identify an initial phase where no lactic energy is needed to meet the energy demand at the beginning of the sprint. Moreover, in addition, by factoring in the measured oxygen uptake over time, we can adjust VLMX for lactate clearance, giving us a likely better estimate of the real maximum glycolytic rate. So now let's take a look at our results. Firstly, we found a mathematically plausible solution for each athlete. The resulting data showed VLMX values ranging from, in this sample, 0.6 to 1.2 millimole per liter per second. The kinetics revealed a time to peak between 6 and 12 seconds and a half-life of the PCR kinetic, which is likely associated with T-ALEC, ranging from 1 to 5 seconds. When we now compare the VLMX from the gold standard method, the 12-second sprint in our case, with the value predicted by our model, we see a systematic difference. This could mean that the model lacks validity or that the gold standard itself systematically misjudges the true value. However, the strong linear correlation between the two data sets suggests that there is at least a significant link between them. To examine the model validity more closely, we then compared the delta BLC from the gold standard, the 12-second sprint, with the value predicted by our model for the same exercise duration. Unlike the VLMX comparison, here is no meaningful difference. The model closely matches the measured value with a standard error of estimate of just 0.4 millimole per liter. If we now look at the time point at which VLMX is reached according to our model, it systematically differs from the fixed 12-second exercise duration used in the gold standard. These findings suggest that the gold standard may consistently underestimate the true VLMX, likely due to its non-individualized exercise duration. In our sample, the average underestimation of the true VLMX is about 10%. So what's next? Unfortunately, there doesn't seem to be a clear, simple relationship between the time to reach VLMX and easily measurable performance indicators that would allow us to cluster athletes in advance. However, comparing the parameters PCR and the optimal pedaling rate appear to have the strongest predictive value for the time to peak. Nevertheless, in line with your findings, Michael and Jamie, we found that a sprint duration of around 9 seconds seemed to be optimal on average. There is also a 4-second window around this peak where at least 90% of the maximum glycolytic rate is active, and a smaller 2-second window of at least 20 and 95% activation. This high activation window can probably guide the choice of sprint duration when applying the gold standard, especially since the influence of TLAC on the calculation becomes stronger as the sprint gets shorter. In this context, it also appears possible to estimate TLAC in advance using individual characteristics and key performance indicators that can be assessed beforehand. So what should you take home? First, we can estimate VLMX from just one maximal sprint using the energy share approach combined with a dynamic efficiency. In professional track cyclists, in our sample, the peak of lactate formation happens within 12 seconds. On average, VLMX is reached after about 9 seconds with a 2-second range where we see at least 95% of the peak activation. Therefore, maybe a 10-second sprint could be a good balance between hitting the peak and keeping errors from TLAC estimation low. And lastly, we can probably get a better TLAC estimation by using individual data that we can collect before testing. Thank you very much, and now I'm open for your questions.
Excellent. Thank you very much for that, Katarina. That's really interesting. Really nice to be able to see that we are building a bit of a consensus within the test duration, as I think that's potentially now the third or fourth study that's now sort of highlighted that 9 to 10 seconds test duration is the optimal going forward. So starting to build a bit of a consensus, which is really nice to see. So we do have a couple of questions coming in. So one from Jamie. So how did you calculate the correction factor for the rate of glycolysis using VO2 to determine the lactate clearance? I think that was in one of your figures earlier on.
Yes, I go back to the slide. Yes, here you see the difference between VLMX and the glycomax, and the idea was that we know the instantaneous VO2 over time, and therefore also now the activation of the aerobic energy metabolism, and calculating the difference between the amount of pyruvate which can be oxidized and the building rate, we get the different values.
Okay, really nice. So I've got one then. So whilst you're on that, you've got the alactic time period of between 1 and 5 seconds. Obviously, we all know that there's quite a big variation in that. Obviously, that can massively have an effect on the reliability and validity of the test. So what method would you use to determine the alactic time period going forward, or how can we better understand what that alactic time period is or should be?
I think it's a very difficult to answer question, and I really don't know the perfect solution. I'm still searching for it. I tried different methods. One of my method was to define it as the first systematic deviation from the fatigue-free force velocity profile to solve the problem of resistance and pedaling rate and so on. That works quite well, but the main problem is you have to do the test with high professional sprinters to get good results. They must be able to activate maximally immediately at the beginning of the test. If that is not the case, you can't use this method, and you can alternatively use a fixed value or use a statistical prediction model. But I'm not sure if we are or will be able to solve the problem before some devices will solve it for us.
Yeah, I agree. I think the variation between elite populations and your amateur recreational populations are going to be quite difficult to determine that true lactate time period. Oh, excellent. Perfect. Well, thank you very much for your presentation. Really nice, really well. I really liked your figures throughout. I think they were really clear and concise. Excellent presentation.